The next problem I want to look into that is that the previous problem we had was how it's gonna the capacitance, the capacitors become discharged through the resistance. Now we want to see how we can charge the capacitor uh, in the RC circuit. So assume that we have a circuit like this. So there's a battery that has a voltage of S, the source voltage, and then it's connected like that. So there's a key, and then there's a resistance, and then there's a capacitor in that resistance, after that resistance, and then it's going to be closed. So initially we assume that there is so this is what we assume that we have initial. So we want to see what's happening. So initially there's nothing there. The capacitor is completely discharged. There's no energy in that. And then we have the R and the C. And then we know that we want to see that after we close the key, if this is a key that we have here, if there's a key here, if we go ahead and close that key, I go ahead and close that key, I want to see how that capacitor is going to be charged. So from completely empty, doesn't have any charge in it, it's going to start to charge, and we want to see how it's going to charge. And it's going to be charged over time. It's not going to charge instantly. So we want to see how it's happening. So if the voltage in that capacitor is VC, and it's going to be function of time, basically this is what we want to find. How much is going to be the VC changing after I close the key. Again, if I look at that, what I would go ahead and do that, I would do it as the node voltage method. So assume this is going to be my reference method, and then here is my node, and here I'm going to have two current leaving. So it's going to be I1 is leaving the node, also the I2 is leaving that node. And the voltage in that node, again, because the is connected one is capacitor, one end of that is connected to the source and the other end is connected to that. The voltage here is the same as the voltage in the capacitor, because the other end of the capacitor is connected to reference. We consider it as 0, so the other end should has the same voltage as the capacitor voltage, because it's going to be the voltage capacitor is difference between the voltage of its two ends. So if we write the node voltage method here, start to write it from here. If I write the node voltage method for the top node here, so if I write the KCL at top node, I know that the sigma I should become 0. So therefore here I know that the I1 plus I2 should be 0. And again, I know from Pearson that the I1 for the capacitor, so I'll not write it here for, I know that the I1 for capacitor is, we had the equation before, is C, if I write it there, for capacitor, we know that the I, let's write it a little bit back so I can, for capacitor. We know that the I is C dV over dt. So I'm going to replace that here. So I'm going to write the C dV over dt. So that's the I that goes through the capacitor. And the I2 that goes through the resistance like before. So it's going to be VC, this time with the other end. So the voltage at the other end. So if it's a VC here, voltage here is going to be Vs, because again, we have connected the battery source. One end of the battery is to the 0. So the other end should be Vs, because the Vs here in the battery shows the difference between the two ends of the battery. So one end is 0, so the other end should be Vs. So the I2 is the voltage at the start minus voltage at the end divided by resistor. That's what we have in the node voltage method. So it's going to be I2 is going to be VC, voltage at the start minus voltage at the end, divided by R, and this is going to be 0. And now if I go ahead and again I times everything and rearrange that, what I'm going to have is that times everything by R and take the Vs to the other side. So I'm going to have RC dV over dt, and then I have plus the V, so also this is the VC. So it's going to be D, and it's going to be VC is equal to Vs. So again, I have the differential equation here, and I want to find the solution to that differential equation. So the solution to that differential equation, we know is going to have the form of the solution for the differential equation for the equation that we have for that is going to be K1 plus K2 e to the power of st. So this is the original equation that shows how the VC is going to be charged through that circuit. So that equation 1 is the differential equation, shows how the VC is charged over time. And the equation 2, we will have it from the differential equation, is the solution to equation 1. And in that, so K1, K2, and S are unknown. To find this solution, we have to find K1, have to find K2, and we have to find the S values. So to do that, again, the very first step that we are going to do is that we know the equation 2 is the solution in equation 1. So if I substitute equation 2 in the equation 1, it should satisfy equation 1, because this is the solution. If it is the solution, if I substitute in equation 1, it should satisfy equation 1. So if I put or substitute equation 2 in 1, what I'm gonna get is that it's gonna be RC, and then I have the d over dt of K1 plus K2 e to the power of st, and then also this one is going to be K1 plus K2 e to the power of st is equal to Vs. So if I substitute that, that's what I'm going to get. And then if I again solve it, so I'm going to get the RC, and for this part the K1 is going to go away. I'll have it's going to be K2 S e to the power of st, and plus K1 plus K2 e to the power of st is equal to Vs. So that's the equation I'm going to get. And if I'm going to rearrange that equation to simplify that equation, eventually what I'm going to get is going to be 1 plus RCS k2 e to the power of st plus k1 is gonna becomes vs equal to vs. Now, if you look at this equation, what we have is that to satisfy this equation, so we have on the right hand side, this one is going to be constant. So this is constant. This part is constant. So this part is also constant. And this part is time dependent. So it's going to be time dependent. So if we want to satisfy this equation, because these two are constant, the only way that this equation is going to be satisfied is that the time dependent part should be 0. Otherwise, if the time dependent part keep changing and changing, there's no way that you have the other part constant and one side is changing, one side is going to be constant. So the only way that is satisfied is that this time dependent part should become 0. And if that part should become 0, what we will get is there are two things that we'll get. The first one we'll get is the 1 plus RCS should become 0 if we want to satisfy this equation. And second, we have to get this constant should be equal to the next constant. K1 should be equal to Vs. So from the first part, also we get the S is equal to -1 over RC. So these are the two. If this equation, if to be satisfied, the time dependent should be 0. So this constant should be 0 because this is a time dependent term. This part is not going to be 0. So that this front coefficient should be 0. And then these two constants also should be equal. So to satisfy this equation, these two should be met. In other words, the K1 should be equal to Vs, and the S should be equal to -Rs. Now that we have the K1 and S, we have to go ahead and find the K2. So again, we know that at the beginning, when the time is 0, at the very beginning, we know that there is no voltage in that capacitor. So the voltage in the capacitor should be 0. So right after I close so I would say that right after I close the T, the voltage in capacitor still is 0. Right after I close it, it still is not charged. As soon as I close it, still is not charged, so it's gonna be 0. So if I put in equation 2, because this is our solution, so I know at the t0 that V should be 0. Right after I close it, at t is equal 0, this should become 0. So if I go ahead and replace that with 0 at t is 0, what I'm going to say that I know that, so the 0, I know in that the VC0 should be equal to K1 plus K2 e to the power of S times 0. The T is 0. And at the T0, VC 0. I replace that. So this is our initial condition. I use that in initial condition. And therefore here, in that equation, I know the K1, I know the S, so I can go ahead and calculate the magnitude of the K2. So if I go ahead, the K1 is Vs, so 0 is equal to Vs plus K2, and this is e to the power of 0, so it's going to be 1. So that e to the power of 0 is 1, so that's what we have. Therefore, the K2 is become equal to negative Vs, if I'm right. So if I have this right now, so if I go ahead and substitute K1, K2, and S into our solution, into the original, the equation 2, what I'm gonna get is that uh, um, I'm gonna get the VC over time is gonna be called Vs minus Vs e to the power of negative T divided by RC. And again, if we consider that tau is equal to RC, what we are going to get is that the VC over time is going to be the Vs minus Vs e to the power of negative T divided by negative T divided by tau. So this is the equation shows that how the capacitor would be charged in a RC circuit. So eventually, if we go back again here, if it's 0, and then when we connect it to the battery, it's going to be fully charged until it gets to the steady state condition. So it is how it's going to happen. So in this equation that we have two terms. So these terms here, this is the steady, it shows the steady state condition. Sorry, steady state condition. That is what eventually it's going to be. And this part, or is going to be transient response of the circuit. So this is the part that is time dependent, and this is the part that is not time dependent. Is eventually this is the value that eventually we are gonna get to that, and I'm gonna show you how it's gonna be. So if I again draw this equation, over time. So if it's gonna be the T, it's gonna be the VC, the voltage at the capacitor. Eventually, if we start at the T0, so there is no voltage in that, and then over time, it's gonna increase until it reaches to its steady state condition, and there is where it's gonna becomes Vs, which is the steady state condition. So that's how it's gonna change. So it, and this part until it reaches to that steady state condition, this part is the transient part, and then that part is going to be its steady state condition. So very quickly, if I want to go over what we talked about, that assume we have the capacitor is completely discharged, and we want to charge it, and so to charge it, we connect it to the R circuit, to the resistance and the battery. As soon as we close the battery, the key, the battery starts to charge the capacitor. So its voltage initially is gonna be 0, and then eventually it's gonna be charging, and its voltage is increasing until it's become fully charged. So to solve that, we write the node voltage method for the very top node here, and then when we solve it, we comes out with the differential equation that shows the change of the VC in this circuit. The solution to that differential equation is this equation 2. This is our solution. We know that it's the format the solution has. K1, K2, and S are unknown, and we want to find it. So the first step to find them is that if this is a solution, should satisfy the original equation. So we put the solution into the original equation and we solve it, and eventually it gives us the K1 and S. And then we need to find the K2. To find the K2, we go to the initial condition. We know that initially the voltage at that capacitor should be 0. So we know if the T is 0, the VC should be 0. So we substitute that. So we know at T is 0, the V is 0. We substitute in that, and it gives us the K2 values. And then we have, when we have the K2 values, we can substitute, and eventually this is going to be our what we have here is the solution that has two parts. It has a steady state part and it has a time dependent part. The steady state part is when it shows the condition that when the capacitor is fully charged, and the transient part or time dependent part shows the condition that the capacitor is completely empty, and it goes into the transient until it becomes completely fully charged. Now let's look at an example of the RC circuit. If we charging the RC circuit. So assume we have the source connected to circuit, so it has one resistance here. So it's going to be R1 and 100 ohm. And then we have the key, which is open before we do anything. So the key is open. Then there's another resistance here. It's the R2, and it's going to be 50 ohm. And then we have a capacitor parallel to that. So that capacitor is C and has a 3 microfarads. And it has the voltage in that is VC over time. So assume this and this one is 15, so the voltage is also 15 volt. So that's the circuit we have, and the key is open for t less than 0. So if the key is open here, so this left part of the circuit, nothing happened that because it's open, and this right part of the circuit, if there is any charges in that capacitor, it's going to be discharged through that resistance here, through that R2. So because the key is open, for sure we know that the capacitor is completely empty, because if it had anything in there, it's already discharged through this R2. So now if we have this, and then we go ahead at the time t is equal to 0, we close the key. So at time 0, we close the key. And when we close the key, it starts to charge the capacitor. So the capacitor starts to charge. And the voltage in capacitor starts to rise from 0 to some final value. So we want to see what's happening in the voltage in the capacitor, how it's going to be changed. So to do that, what we had in previously is that we learn how we can charge the capacitor through a single resistance. So we have somehow changed this uh, circuit to have only a single resistance, and then we can use whatever uh, method we use up to this point. So to do that, we want to replace this with a circuit that is going to be like that. So we want to have this single source, and then we want to have a single, so if that's our key, so let's draw it the same like that. So if it's going to be there, so we want to have a resistor, and after we close the key, we have the key also here, and the capacitor here. We want to replace this one with this one, because this is the one we learn how to solve it. This is the one we learn how to actually we can as I would say, this is how we know how to charge the capacitor through a single resistance. So we'll have to convert this one to this one. So if we I compare these two together, and what I can say is that if I go ahead and assume after the T0 is going to be closed, so these two, I want them to be the same. So look at here, if I come here and say, assume I call this point A and this point, this node here B, and then I come here and say, okay, this is the A and this is the B. Therefore, whatever, or let me just draw this a little bit further away. So it's easier to show it. Let's bring them a little bit further away here. So it's going to be our capacitor here. And it's going to be that 3 microfarad. And we see over time. So now if I consider this part, so if I consider this part here, and I replace that part with this one here, so basically if I replace this box with that box, I'm gonna be okay. And if you look at these two, you will see that this green box here and this green box here, the green box here is a Thevenin circuit for this circuit. So it's gonna be, assume I have a circuit with two terminals, A and B, and then I want to replace this circuit with a single source and single resistance. So it's going to be the Thevenin circuit for that circuit. So if I can do that, I replace the equivalent Thevenin of, I replace this circuit here with its equivalent Thevenin, Then I have the standard charging capacitor through a single resistance. So I can use the equation I know before. So to find this one, I have to go and find the sources and the resistance here. So remember when we had the Thevenin, to find the Thevenin resistance, the easiest method was that if we didn't have any dependent sources, which we don't, we could zero the sources, and then equivalent resistance would be the same as the Thevenin resistance. So if I zero the sources uh, in this one, zero sources. So when we have the voltage, if I want to zero the voltage sources, you just replace it with a single wire. So it's going to be something like that if I zero the sources. And we had this example before. If you want, you can go back and look at that when we talk about the Thevenin, how we did that in detail. So it's going to be 100 O, and then we have this resistance here, which is going to be 50 O, and then we have these A and B. And then if you look at it from this point and calculate the RT, so the R equivalent, so if I call this RT, the Thevenin, the Thevenin resistance is equal to R equivalent for this system, which is, if you look at here, both end of the one end of them are connected to one another, the other end also connect to each other. So assume I can move this, because I can move it along that wire, so I can move that resistance up here and bring it here. Then you will see these are parallel to each other. So I have two resistance parallel to each other. So the equivalent is going to be 1 over 100 plus 1 over 50, which if we do the calculation, we will get the 100 divided by 3. So it's going to be our Thevenin resistance here is going to become 100 over 3 O. And then we need to find the source, the voltage source here. So that was the first part that we did. So this is the RT. And then for the second part, what we need to do is that we have to go and find this voltage source. So to find the voltage source, remember that we will use the short circuit. So if we go ahead and use the short circuit condition, so it was that, then we have these 15 volts is going to be here. Sorry. So yes, so that's going to be that 15 volts here. And then we have the that 100 ohm here. And then we have that 15 ohm here. And then we have the A and B. And then we short circuit them. So, and whatever current goes through that is what the ISC. The current goes through that. So if you look at this circuit right now, you can see that because we short circuit this resistance, all the I goes through, there's no I go through this leg here. So the I here is going to be 0. Nothing goes there because we short circuited. All the current just bypass that. So it's going to become a very simple circuit. So we have one source, one resistance, and the current goes through that resistance, go through A, B, goes back. So nothing goes through that. And because of that, so the ISC, we can calculate the ISC very simply, it's just Ohm law. So if I, for example, write it for this one, the old law V is going to be IR. So the voltage we have is 15 volt, because that resistance connected to this. So the voltage is 15 volt across that, and the I is ISC, and the R is just 100 ohm. That we will have. So therefore the ISC is 15 divided by 100. So that's the ISC goes through that circuit. And then if I come here and look at this circuit, what I have here, so we know that in that circuit, if I connect the A and B together, and then I'm gonna have the ISC go through that, and then have a RT, so I can calculate the VS here. So again, if you go back in, so I will write it here. So if I draw this circuit here and short circuit that, it should be equivalent to this one. So the short circuit of that is the source that we don't know what it is. We have the RT, which is 100 divided by 3, and then we have the A, and we have the B. So this is what we want to be as equivalent to this one that we have here. We keep the capacitor the same. So if I connect these two, because this should be equivalent to that, so that should be ISC as well, which is 500 divided 15 divided by 100. So in this circuit, I write the Ohm law again. So the voltage is going to be the voltage of Thevenin. We don't know that, so it's going to be the voltage of Thevenin. The I is 15 divided by 100, and the R is 100 divided by 3. So it's going to, so these two will cancel each other, so it's going to be 5 volts. So we have this one is going to be 5 volt. So now we find the equivalent of this circuit to this one. So this is right now what we have. It's a simplified, it's a simple circuit that has the source, single battery, and a single capacitor. And we know how to solve that. We previously worked how to do that. So if I go ahead and redraw that circuit again, now that we have the V is 5 volt, and then we have the R T, which was 100 divided by 3, and then we have this, we have that, we have the capacitor, 2 microfarad, and VC, and this is what we have. So now if I close the key at t is equal to 0, we want to see how the V is gonna change. And we know from the previous solution, when we solve that circuit for general condition, we know that the change in the VCT is gonna be the VS minus Vs e to the power of negative t over tau that we have. So we know that the Vs is the voltage of the source, so it's going to be 5 volt here, and we know the tau is RC. Last time when we work on that, we said that the tau is going to be R times C, so it's going to be, the R is going to be 100 divided by 3 times 3 times the 10 to the negative 6, so it's going to be the RC that we have, so it's going to be 100 times to the negative 6 that we have, or times, or just simply 10 to the negative 4, can simplify it further. So if I replace these two together, so the change in the change of the voltage in the capacitor is going to be the Vs, which is going to be 5 volt, minus the Vs, then it's going to be 5 times e to the power of negative t divided by 100 times 10 to the negative 6. Well, let me write it. Negative t divided by 100 times to the 10 to the negative 6. So this is going to be how the voltage in this circuit is going to change for t just equal or larger than 0. As I remember, I was talking the last time, this part of the equation, the first part, this one is going to be the steady condition, which is going to be a steady state condition, which shows that eventually this is what the voltage is going to become equal. So we have the 5 volt battery, and we know eventually if we keep the key closed for a very long time, eventually the current in the capacitor becomes 0. It doesn't let any current go through anymore, and the voltage in the capacitor is going to become equal to the voltage to sources, because when we don't have any current goes through that circuit, the voltage in the resistance becomes to 0 based on the Ohm law. If there's no current, there is no voltage here. So the voltage here is become equal to that. So this is the steady state condition, or this is what eventually we are gonna get to that condition. This part is the transient response, is, if you would say so, or transient condition. Let me make that also response. Response. So this part is what's happening between the time that we close the key up to the point that we eventually get to final condition. So this part eventually becomes 0 and fade away. If you draw it, you will see the effect of that part. It goes away. Eventually, the VT is that. So this shows the long-term condition, what's happening after we keep the key closed for a long time. The second term shows what exactly happened right after we close the key until to the point that we get to the steady state condition.